Hello everyone, welcome to the YouTube channel of YourPedia Engineering Career Point. So I am Vinesh Sharma, your mentor of mechanical engineering here. So as you know, the Oil India Limited and BEML has announced the vacancies here, and we have started the module regarding that, and the classes has been started. Okay, and almost the thermodynamics has been finished, and now we are going to move toward the next step here, that is RAC here. Okay, and in these YouTube videos here, I am just solving the practice questions here related to the Oil India exam limited separately, as well as the BEML exam separately here. Okay, so in the last lecture we have done the solutions of some of the questions related to the thermodynamics here, as well as the heat transfer. Okay, now what I am going to do in this particular video, we are going to see the questions of the heat transfer subject here, specifically for the BEML here. Okay, Bharat Earth Movers Limited, we are going to see the heat transfer important questions. So there are only 20 questions where I am going to solve it right now. So just make sure that you just see the video completely. Okay, and just pay attention carefully. Okay, so let us start here without any delay. So here we have our first question. In the first question, what is given to us? A thin copper wire at 300 degrees Celsius is suddenly immersed in a water at 30 degrees Celsius. Okay, it cools down to 150 degrees Celsius in 70 seconds. Okay, it is then reheated to the initial temperature of 300 degrees Celsius, and it is suddenly exposed to the air at 30 degrees Celsius, where it cooled down to 150 degrees Celsius in 200 seconds here. Okay, where there is a difference in the cooling time, we have to mark. So first of all, just see the copper wire initial temperature is 300 degrees Celsius here. Okay, and it is cooled down to 30 degrees Celsius. In both the cases, you are cooling down the rod from 300 to 30 degrees Celsius. Okay, in the first case we are using the water to cool down the rod here, and in the second case we are using the air. So now you can see, observe the data very carefully. In case of water, it is taking a time of 70 seconds, whereas in case of air, it is taking a time of 200 seconds. That means the cooling rate is very slow in case of air. That is why it is taking a large amount of time. Okay, but why there is a variation here? So first of all, you have to understand that in both the cases, which mode of heat transfer is dominating here. Along with that, we can see what are the different parameters on which it is depending upon. Okay, so first of all, here in both the cases, the convection mode of heat transfer is dominating one, and we know from the Newton law of cooling, the convection heat transfer coefficient is given by HA delta T. Okay, so correspondingly, the outer surface area of the sphere as well as the temperature difference are same. That means the only parameter which is creating a difference here, that is the heat transfer coefficient. And the heat transfer coefficient generally for the liquid case here is higher as compared to the gases here. Okay, whether it is a case for a free convection as well as the forced convection here. Okay, that is why we have seen that the cooling rate is very much higher in the case of water as compared to the air. Okay, so now you can see here why we have this difference here, because of the large heat transfer coefficient in the case of water as compared to the air. That is a correct answer here in this case. Okay, so that's a very simple case. Now let us move toward the next part. In the second question, what is given? A fin of length L, capital L, protrudes from a surface held at a temperature T0 greater than the ambient temperature TA here. So here we have a fin. Let us say it is connected to a plate here. Okay, so on the plate, or I can say the root side, the temperature is T0, and correspondingly the surrounding temperature is given to you as TA here. Okay, TA is the surrounding temperature. Now what is the heat dissipation from the free end of the fin, which is assumed to be the heat dissipation from the free end of the fin is assumed to be negligible here. That means there is no heat transfer taking place from the tip. Okay, there is no heat transfer taking place from the free end of the fin, or I can say it is a adiabatic fin case here. Okay, adiabatic tip case is there. Now what will be the temperature gradient at the fin tip? First of all, we have to find out. So now you can see the temperature gradient at the fin tip we have to find out. Now what is the meaning of temperature gradient? The rate of change of temperature. Okay, so first of all, if you just see here, it is a case of a adiabatic fin type. So I can say at the tip of the fin there won't be any heat transfer. So correspondingly, if I go through the Fourier law of heat transfer here, I can say the value of the minus Ka dt by dx at x equal to L here, it will be equal to 0. It will be equal to 0. So now you can see what will be the temperature gradient at the tip here. So I can say the temperature gradient at the tip will be equivalent to 0 here. Okay, so that is a case. So I can say the option number A will be the correct answer in this case. So that's again a very simple case. Okay, it is not so much difficult for you. Coming back to the next question. Following ways have been suggested to increase the effectiveness of an infinity long fin here, using fin material of high thermal conductivity, increasing the ratio of the area to parameter of the cross section of the fin, increasing the convective heat transfer coefficient, increasing the ratio of the parameter. First of all, if you just see, what is the meaning of effectiveness of the fin? Effectiveness of the fin are basically the term which is related to the performance of the fin here. Okay, it is defined as the heat transfer through the fin, okay, to the heat transfer without the fin. So whether you have to install the fin over a surface or not, we have to we found that condition with the help of this effectiveness parameter. Okay, so if the value of this effectiveness is more than 1, then we say that we have a benefit of using the fins here, otherwise we don't have any benefits here. Okay, so now the effectiveness formula can simply be written as Pk upon Ha here. So from this expression you can just answer this question here. In the first part, using the fin material of high thermal conductivity, so now you can see the effectiveness is directly proportional to the thermal conductivity here. So higher the thermal conductivity, higher will be the effectiveness here. So option number A will be the, statement number A is the correct one here. Increasing the ratio of area to parameter of the cross section. First of all, effectiveness is directly proportional to parameter by area. Okay, so now you can see if you are increasing the ratio of area by parameter, in that case this value will decrease and correspondingly effectiveness will decrease here. Okay, so I can say the statement number B is wrong here. So now you can clearly see, you can eliminate the option number B, C and D here. So therefore the option number A will be the correct answer. Okay, let us read the statement number C and D also. Increasing the convective heat transfer coefficient, again you can see here effectiveness is inversely proportional to the heat transfer coefficient here. So we have to use the fin in those cases where the value of the heat transfer coefficient is very low. Okay, that is why we prefer the fin in the case of the air cooled IC engine as compared to the water cooled IC engines here. Okay, next part, increasing the ratio of the parameter, that is the correct one here. So option number A will be the correct answer of this part here. Next question, for which of the given conditions heat transfer from the insulated tip can be considered as a case of a can be considered as a case of a fin of a finite length here. Okay, so in this case just see, first of all we have to mark the conditions here. Okay, so in this case you can assume the heat transfer from the insulated tip can be considered as a case of the finite length here. Just see, so this can be solved by checking out the value of the ml here. Okay, so if you just check the value of the ml in each of these cases here, you will find this value is coming out to be around 2.25, this value is coming out to be as 2.16, this value is coming out to be around 2.4 here, and this value is coming out to be 3. Okay, so higher the value of the ml, so that fin can be considered as a case of a fin of a finite length here. So option number B will be the correct answer. So that is basically a little bit by the way, it is a easy questions here. Okay, just by checking the value of the ml you can just predict that in which case we can consider the insulated tip as a case of finite length. So you have to just remember the condition that the value of the ml should be more here. Okay, now coming back to the next part, the boundary conditions which describe the process of conduction between the two bodies in the perfect contact is known as the boundary conditions of the first kind, boundary conditions of the second kind, as well as the boundary conditions of the third kind here. So basically here in this case, the boundary conditions which describe the process of conduction, it is basically best described by the fourth kind here. Okay, so option number D is the correct answer here. Now the next part, Nusselt number is equal to constant multiplied by Reynolds number to the power m. Nusselt number is equal to constant Reynolds number to the power m, Prandtl number to the power m. Okay, in this case, what does for which case this equation is written as here? So first of all you have to understand that whenever we are studying the convection, there are two cases, free convection and the forced convection here. In the case of a free convection, we have a Grashof number, we don't have a concept of Reynolds number there because velocity does not play any role. Whereas in the case of force convection here, we have a role of the Reynolds number because the velocity plays a significant role here. Okay, so I can say this is a case of a force convection here. Okay, so that's a very simple case, and depending upon that whether you are studying the case of a flow through pipe or a flow over a flat plate, you can find out the exact value of the M as well as the N here. Okay, you can find out the exact value of M as well as the N here in this case. Now coming back to the next part, what is the relationship between the rate of convection heat and the rate of mixing in turbulent fluid flow represents? Okay, so here you can see what is the relationship between the rate of convection heat and the rate of mixing in the turbulent fluid flow. Let us start with the options here. The rate of convection heat transfer coefficient decreases with increase in rate of mixing in the turbulent fluid flow. So I can say, just see first of all, as you are increasing, first of all the heat transfer coefficient is not a thermodynamic, I can say it is not a thermometric property here, okay, because it depends upon many parameters depending upon whether the flow is in free convection or a forced convection here. Okay, in the case of free convection we have a different parameters, in a case of a forced convection we have a different parameters here. And in this case, if you just observe very carefully, the rate of convection, as you are increasing the rate of mixing here, as you are increasing the rate of mixing, at that point of time the heat transfer coefficient is also going to be increased here, it is not going to be decreased. Why? Because the mixing is going to induce, or I can say it is basically increasing the thermal diffusion rate among the fluid layers here. So correspondingly I can say the option number B is going to be the correct answer in this case here. Okay, so that you have to remember. Now coming back to the next part, for fluid flow over a heated plate, the following properties are given to us. Okay, the hydrodynamic boundary layer thickness at a specified location of the plate, if 1 millimeter the thermal boundary layer thickness at the same location is. Okay, so here what we have to find out, we have been provided with the value of the boundary layer thickness and we have to find out the thermal boundary layer thickness here. So in this case, what parameter we are going to choose? We have to calculate the value of the Prandtl number, because the Prandtl number is only a property of a system here, or I can say it is a dimensionless number which relates the thermal diffusion rate with the momentum diffusion rate here, or I can say it basically compares the thermodynamic boundary hydrodynamic boundary layer with the thermal boundary layer here. Okay, so correspondingly what is the formula? It is written as mu by alpha, or you can write mu Cp by K here. Okay, or further it can be written as del by delta T to the power cube here. Okay, now coming back to the here, so first of all we have to find out the exact value of the Prandtl number. So we know the value of viscosity, specific heat as well as the thermal conductivity. So therefore I can say Prandtl number is equal to viscosity multiplied by specific heat divided by thermal conductivity. Okay, so now you can see Prandtl number is coming out to be 1. Therefore the value of the hydrodynamic boundary layer thickness as well as the thermal boundary layer thickness, they are going to be remain same. So therefore the option number C is going to be the correct answer here in this case. Okay, so that's again a very simple case here. Now next question, a thin metal plate is insulated on the back and exposed to the solar radiation at the front surface. The exposed surface of the plate has an absorptivity of 0.6 for the solar radiation. If the solar radiation is incident on the plate at the rate of 700 watt per meter square and the surrounding air temperature is 25 degrees Celsius. So here we have a plate. Now you can see, so this bottom plate is not exposed to the sunlight here, the top surface is exposed here. Okay, now correspondingly the absorptivity is given to you 0.6, and the next thing is determine the surface temperature of the plate when the heat lost by the convection and the radiation equals the solar energy absorbed by the plate. So now I can say the heat lost by convection plus radiation, okay, it is equivalent to the heat absorbed, and these two parameters are directly related by the combined convection and radiation heat transfer coefficient. So I can write HA surface temperature minus ambient temperature is equal to heat absorbed, which can be written as alpha times heat entering over the surface here. Okay, this expression can be written here. Now in this case you can also multiply it with the area here. Now the area will be cancelled out. Correspondingly the value of H is given to us 50 and the surrounding air temperature is given to us 25. Correspondingly 0.6 is the absorptivity and the total heat absorbed is the total heat incident radiation is 700 watt per meter square. So correspondingly you can see the temperature value will be 0.6 multiplied by 700 divided by 50 plus 25. Okay, that will be the final expression you are going to see. So if you just solve this problem, you are going to get the final answer as 33.4 degree Celsius. So that's again a simple case. Next question. A small sphere of outer area 0.36 meter square, it is totally enclosed by a large cubical hail. So here we have a cubical box. Inside this cubical box we have a small spherical sphere here. Now the shape factor of the hail with respect to the sphere is, so let us say the cube is 1 and the sphere is 2. So I can say the value of F12 is given to you as 0.008 here. Okay, now the next thing is what we have to see, the measure of the internal side of the cubical hail is. Okay, so we have to find out the dimensions here. We have to find out this particular dimension. How can we solve that? We have to use the reciprocity relation here. So I can say the value of A1 F12 is equal to A2 F21. I can write the expression in this way. Now correspondingly area 2 is given to you as 0.36 meter square. F21, it is going to be 1 because all the radiation incident from the sphere is going to be strike the block here. Correspondingly the value of F12 is given to us 0.008 and the area of the total area of the cubical box can be written as 6a square, where a is representing the side of the cube. So if you just solve this expression, you are going to see 0.36 divided by 6 multiplied by 0.008 under root. This is the final expression you are going to see here. Okay, and the final answer of this question will be equivalent to 2.74 meter here. So just solve it and get your final answer, that is 2.74 meter. Okay, so level of in this case you can see a number of numerical question may be more here. Okay, and the level of the numerical question is not so much difficult, it is going to be moderate only. Okay, so you can solve this problem very easily. Next part, a radiator on a space capsule must dissipate heat generated inside the capsule by radiating it into the space. While on the bright side of the earth, the capsule sees the earth radiations and the solar radiations here. The radiator surface has a solar absorptivity of 0.5 and emissivity of 0.9 here. Solar absorptivity is given to us 0.5 and emissivity is given to us 0.9 here. Now what is the maximum equilibrium surface temperature of the radiator if the maximum heat generated in the capsule, it is 800 watt per meter square Kelvin here. Okay, that we have to find out. So first of all, just see in this case what is given to us. We have been provided with the capsule here. Okay, now on one side of the capsule we have a earth, on the another side of the capsule we have a sun. Now from this sun to the capsule, how much energy is going to be entering here? So it is given to you 524 watt per meter square. And from the bright side of the earth to the capsule, the total radiation is 100 watt per meter square. 100 watt per meter square is given to us. Okay, so this one is the capsule. This one is the capsule here. This one is the sun here, and this one is the earth here. And the total amount of incident radiation of the capsule is given to you. Now in this case, what we have to find out? We have to find out the equilibrium surface temperature of the radiator here. So what we have to do? We only have to do the energy balance in this case. So if you just solve the problem here, so you can see absorptivity is also given to us 0.5 and correspondingly emissivity is given to us 0.9 here. Just give me a second here. Yeah. Okay. So now you can see, if I just simply balance the energy here, so I can write the maximum energy generated. Okay, so now you can see 800 is the total maximum energy which is being generated inside the capsule due to the solar radiations as well as the radiation coming out from the earth here. Okay, which can be written as epsilon sigma T4 minus 0.5 multiplied by 524 minus 100 here. Why I am writing this equation here? Because this equation is representing this first term is representing the energy emitted from the capsule to the outer space. These two terms are representing the energy which is being incident on the capsule here. Okay, so this is the energy out, this is the energy in. And after putting all the values into this expression, you are going to get the final answer. So epsilon is given to you. Epsilon is 0.9 here. Stephen-Boltzmann constant is 5.67 into 10 to the power minus 8. Temperature is around, temperature we have to calculate here. Okay, so this is absorptivity multiplied by 524 minus 100 here. Okay, so just solve the do the calculation here and you will get the final answer of the absolute temperature. So in this case the final answer will come out to be around 400.86 Kelvin there, and you have to mark the answer in degrees Celsius. So you can see 127 degrees Celsius will be the correct answer. So option number C will be the correct answer of this question here. Okay, so that's again a very simple case. Now the next part, an electric flat plate square heater. So here we have a flat plate square heater which is having a dimension of 10 centimeter. Okay, and is providing a 100 watt of power from each side here. From each side you are going to get, just give me a second, it is a square heater na? Yeah, it is a square heater na? So you are going to get the 100 watt power from each side here. 100 from this side also 100 and from this side also 100 here. Now if the heater is assumed to be black, what should be its temperature? Here we have to find out. Okay, so that's again a very simple case here. So now you can see the total amount of radiation emitted from the surface can be written as E is equal to epsilon multiplied by sigma multiplied by area multiplied by T to the power 4. Okay, now in this case, side is given to us 10 centimeter, not 10 centimeter, 10 centimeter, 10 centimeter, 10 centimeter. Okay, so for if you just see from each side, you are going to get the answer here. The area of this square heater is going to be, emissivity is going to be 1, epsilon is going to be 5.67 into 10 to the power minus 8. Area is around 0.1 multiplied by 0.1 here. This will be the total area of the square side heater. Okay, now coming back to the next part, we have to find out the temperature. So it is an unknown quantity here, and correspondingly how much total power is emitting, so that is 100 here. Okay, so this much total amount of energy which is being emitted here is given to you 100. So just by equating this term you can simply find out the value of the temperature T, and it is coming out to be around 648 Kelvin here. 648 Kelvin here. Okay, so option number B is going to be the correct answer here in this case. So even though some questions require some little bit lengthy calculations here, but you should know that how to solve these questions here. Okay, so for example, if you are getting any question like this one, so first of all just see the options. So if your options are very close to each other, just skip the questions here because you are not going to solve it in the time here. But if the options are wide, like in this case, you can see, you can proceed with the calculation. Okay, you can do the approximation and you can get the final, I can say the close answer you are going to get. Next, question number 13. A hemispherical furnace of radius 1 meter has a roof temperature of T1 as 800 Kelvin and emissivity epsilon 1 as 0.8 here. The flat floor of the furnace has a temperature of T2 600 Kelvin, which is having a emissivity as 0.5. Okay, so this is a 1, this is a 2 here, and the temperature is given to us 800. The temperature of 2 is 600 here. The corresponding emissivities are given to us 0.8 and 0.5. The next thing is radius. Radius is given to us 1 meter here. Okay, now what we have to find out? We have to find out the shape factor F12. So the radiations which are coming out from the hemispherical portion and striking the flat floor here. So again, just use the reciprocity relation here. A1 F12 is equal to A2 F21. In this case, you can see the value of area 2 can be written as pi r square. F21 is going to be equal to 1 only, whereas F12 we have to find out, and the area 1 can be written as 2 pi r square. Okay, so if you just solve it, you are going to get the answer as 0.5 here. Okay, now so option number, how much value you are going to get here? Option number C, 0.5, you are going to get the correct answer here. In this question, what is given to us? A 40 centimeter diameter disc with emissivity of 0.65. Just see, first of all, from the radiation part here, you have to just cover up the basics definition of the 5 laws which we cover. Okay, Stephen's law, Planck's law, or the Wien displacement, Lambert cosine law. These 5 law we have to see here. Okay, now the simple numerical can be framed from the Planck's law as well as the Stephen-Boltzmann law. Along with that, the numericals can be framed from the resistance part here, where we cover the 2 type of resistance which we encountered in the radiation problem. The first one is the surface and the second one is the space resistance here. Okay, now in this case, what is given to us? 40 centimeter diameter disc is given to us, emissivity is 0.65. It is placed in a large enclosure at 30 degrees Celsius, and correspondingly the initial temperature of disc is 55 degrees Celsius here, and we have to find out the radiosity. Now what is the meaning of radiosity? First of all, in radiation part there are 2 terms. The first one is the irradiation and the second one is the radiosity. If we just see the radiation radiosity here, radiosity is representing the total amount of radiation energy which is being leaving from the surface here, whereas irradiation is representing the all the radiations which are striking the surface here. Okay, or I can say it is representing the incoming radiations here. Radiosity is representing the outgoing radiations here. Okay, so let us first create a simple free body diagram here. Emissivity 0.65. Okay, emissivity is 0.65 here. Next, large enclosure is given to you 30 degrees Celsius, and correspondingly disc has a temperature of 55 degrees Celsius. Now you can see, due to the emissivity, first of all, due to the temperature of 55 degrees Celsius, some amount of radiation is going to be emitted from the surface. Okay, along with that, we can say due to the finite value of the emissivity, it is also having some reflectivity also, or I can say absorptivity also. Okay, so therefore I can say the value of the radiosity, which is represented by J generally, it is written as emissivity multiplied by the radiation emitted by the black surface plus 1 minus absorptivity multiplied by the do we have a value of the here in this case incident radiation here? Incident radiation is not given to us now. Yeah, so here we can assume, yes, just see, in this case the enclosure temperature is given to us, so I can say from the surrounding some radiation is also acting upon this disc here. Okay, so here we have disc, from the surrounding the radiations are incident here, so some part is going to be reflected and some part is going to be absorbed here. Along with that, due to the temperature of the disc itself, some radiation is going to be emitted from the disc here. So now you can see this is the emissivity of the disc, that is 0.65 multiplied by 5.67 into 10 to the power minus 8 multiplied by 55 degrees Celsius, which will be around 338, I think 328, sorry, 328 Kelvin here to the power 4 plus, now according to the Kirchhoff law, the value of the emissivity and the absorptivity are going to be same here. So I can say 1 minus 0.65 multiply by, what is the value of G? G is the radiation which are incidentting on the surface due to the atmosphere. So I can simply calculate it by the sigma into surrounding temperature. 5.67 into 10 to the power minus 8 multiply by 303 to the power 4 here. Okay, so this is the final expression you are going to get. Now you have to solve the entire expression to get the value of the radiosity here. So in this case you are going to get the answer as 593.84. So it will be around 594 here. Okay, so just solve this entire expression and you are going to get the answer. Again you can solve the questions here, because you can just solve this question in the exam, because there is a wide variation in the options here. Next question number 15 here. We have a two long parallel plates which is having the same emissivity as 0.2 and they are maintained at a different temperatures. So they are not a black body. Now, to what amount will the radiation heat exchange get reduced by the radiation shield of emissivity 0.4 placed in the middle? Okay, so while solving this type of question, just try to create the radiation network diagram here. Okay, and just try to calculate how many resistance are getting induced, included here whenever you are inserting any one shield or any two shields here. For example, let us say we have only two sheets, we have only two plates here, and if they are non-black in nature, how many resistance are going to be there? The first one is the surface resistance of the plate number 1, the second one is the space resistance in between the two plates, and third one is the surface resistance of the plate number 2. Okay, so there are total 3 resistance. Now you are inserting only one shield here. Let us say this red color one is representing the shield. Now what will be the total number of resistance? So here you can see surface resistance of the plate 1, then we have space resistance between the plate 1 and the radiation shield second, then surface resistance of the shield itself, okay, toward the left side, and the surface resistance of the shield again toward the right side, and then we have a space resistance between the shield and the right surface here. Okay, and in the last we are having the surface resistance of the plate number 2. So now you can see by incorporating the only one shield inside between these two plates, we are increasing the total number of resistance by twice here. Okay, so just solve the just do the calculations here and get your final answer. So we have to find out that by what amount the radiation heat exchange has been reduced. So now you can see without shield, I can say sigma T14 minus T24 divided by 1 minus epsilon 1 plus 1 upon F12 plus 1 minus epsilon 2 here. So this is the value of the heat transfer without heat transfer, okay, sorry, without shield, and with shield the heat transfer will be written as sigma T14 minus T24 divided by 1 minus epsilon 1 upon epsilon 1 plus 1 upon F1s plus 1 minus so this is the surface resistance of the shield. Okay, so there are 2, so I am multiplying it with the 2 here. Okay, so now you can see if you just take the ratio of these two terms, the numerator will be cancelled out. Okay, and correspondingly the value of the Shea factors are given to you as 1, and we know the value of epsilon 1, epsilon 2 as well as the epsilon s also. Okay, now So just find out, just put down all the values into this expression, and you are going to get just by how much amount the radiation has been reduced here. Okay, so if you just put all the values, you will find the value of this ratio will come to be as 9/13 here. So it will tell you that by 9/13 factor, the radiation heat transfer has been reduced. Okay. Next question. The effect of scales, deposits, rust formation, etc. formed in the heat exchanger can be taken care by introducing the additional thermal resistance. Yeah, so that is basically a falling resistance here. This effect is known as the falling, and the resistance is being considered with the parameter of falling resistance here, and the unit here it will be meter square Kelvin per watt, or you can write Kelvin per watt here. Okay, so if you are calculating the value of the total resistance here, you have to understand the total resistance will be written as 1/R1 plus falling resistance plus 1/R2. So it is simply added up in the resistance part here. Next, in a heat exchanger, hot gases enter with a temperature of 250 degrees Celsius, leaves at a temperature of 50 degrees Celsius, and on the other side, air enter at temperature of 50 degrees Celsius and leaves at 90 degrees Celsius. What will be the effectiveness of the heat exchanger here in this case? Okay, now just see from the values itself, you can say that it is a case of a counterflow heat exchanger. Why I am saying that? Because in this case, the outlet temperature of air is more than the 50 degrees Celsius here. Okay, so that is why I am saying that it is a counterflow heat exchanger here. Now in this case, how can you calculate the value of the I can say the effectiveness here? So effectiveness is having a direct formula. Okay, so now you can write Q actual by Q maximum here. Q actual by Q maximum. Now you can see the Q maximum will be written as C minimum divided by THI minus TCI here. Actual can be written as CH THI minus THE here. Okay, so just by comparing the heat transfers, okay, just find out that which is having a lower value of heat capacity, then put it down in this particular expression, and you are going to see that what will be the effectiveness here. So that's again a very simple part here. Okay, so I am not doing the exact entire calculations here, so that you can simply do just balance the heat and find out the ratios of the heat capacity, and then put it into this expression here. That's it, and you will find the final answer is coming out to be around. Okay, so just find out the answer here. Okay, so there is some I can say that there is some error in this question here in the options. Okay, so you are going to get the final answer as 1 here only. Okay, the actual heat transfer will come out to be as maximum possible heat transfer only. Next part, water at 80 degrees Celsius enter the counterflow heat exchanger with a mass flow rate of 0.5 kg per second. Air enter at 30 degrees Celsius with a mass flow rate of 2.09. What will be the effectiveness of the heat exchanger LMTD here? Okay, so this is a case of a counterflow heat exchanger. Okay, and we also know the value of mass flow rate of water as well as a Cp here. So let us calculate the value of the heat capacity of the water first. So you are going to see it is coming out to be around 2.09, and if you just find out the value of the heat capacity of the air, you are going to see 1 multiplied by 2.09. Again it is coming out to be around 2.09. So I can say it is a case of a balanced counterflow heat exchanger. Okay, and in the case of a balanced counterflow heat exchanger, the simply 0/0 form is going to be there if you just put it down in the formula. So I can say simply the LMTD will be equivalent to delta Ti or delta Te here, THI minus THE here, sorry TCE here. Okay, so now you can see the water is entering at a temperature of 80 degrees Celsius and the air is entering at a temperature of 30 degrees Celsius also. Okay, so now we have to do the balance here. So if you just solve it, you are going to get the value of the temperature here also. Okay, now? Oh, just give me a second. Just give me a second. We already know the value of the effectiveness here now. So effectiveness is equivalent to, okay, or you can simply write just see, effectiveness is also given to us now. So we can simply say effectiveness can be written as THI minus THE divided by THI minus TCI here. 0.8 equivalent to 80 minus THE divided by 80 minus 30 here. Okay, so from this expression just find out the value of THE here, and it is coming out to be around 40 degrees Celsius. So now you can see the LMTD will be delta TI or delta TE here. So I can write THE minus TCI here. Okay, I can also write in this form. So therefore the value of LMTD will be 40 minus 30, that is 10 degrees Celsius. Option number D will be the correct answer here in this case. Next, consider the following statement. In a shell and tube heat exchanger, baffles are provided on the shell side to prevent the stagnation of this shell side fluid, improve the heat transfer, provide support for the tube, prevent falling of the tube. All the options are correct one here. Okay, so option number A is the correct answer here. Next part, during the process of the boiling and condensation, only a phase change take place and one fluid remain constant temperature throughout the heat exchanger. In terms of the number of transfer units, the effectiveness of such a heat exchanger would be, just remember that whenever there is a phase change in the heat exchanger, no matter what type of heat exchanger you are using, either it is a parallel flow heat exchanger or a counter flow heat exchanger, the same performance you are going to get here. Okay, in this case. So and we have a direct formula in this case, that effectiveness will be equivalent to 1 minus exponential to the power of 1 minus NTU, or exponential to the power of minus NTU here. So that is the final formula here, because here in this case the C is going to be 0, and you can see effectiveness is equivalent to this one here. So if you just put the value of C as 0, you are going to get the option number D as a correct answer. Okay, so these are some of the questions related to the heat exchanger part, heat transfer part here. So these questions are very, very important for you, because it consists of all the portions of the heat transfer subjects, okay, comprising of all the four topics chapters here. Okay, just make ensure that you cover these type of questions here, because it will clear your all the concept as well. Okay, so that's it for today's class here. Now in the next video I will come up with the questions of the theory of machine, okay, for separately for the Oil India Limited as well as the BEML here. So thank you very much.